Hello, and welcome to this short Friday lecture. I will start by saying that now you have a practice test. And what is that? A practice test is a test, it's a selection, if it is not all of them, but it's the weekly tests that you had this fall term. It's the first 9 weeks now. Later today it will be updated with the 10th week, and next Friday at 6 o'clock it will be updated with the 11th week. At 6 o'clock today the current version will be force graded, so you can see what you have done so far, but then again it's open, all of the practice tests, and I urge you to do this, because if you do this, then you know that in 3 weeks' time, Friday the 4th of December, you have a 1 hour test without any aids. But if you can do the practice test, then you know that it will be variance or even just randomized problems that you have seen in the weekly test this fall term. So if you can do this, you can do the 1 hour test without aids. So please do that.
Excuse me?
Yep.
For the 1 hour test, how many questions was it?
It will be like the weekly test. There will be 10 questions.
10 questions.
Oh, I did 10, yeah.
Yeah, okay. From all the different kind of topics you have.
Yeah. It will be a selection, yes. Yeah. Okay. So my talk today will take us through 4 examples, 3x3 matrices, and we're going to look if it's possible. We're going to find eigenvalues and eigenvectors, and we want to see if they can be diagonalized. And I'll tell you what that means. And I'll end up by discussing similar matrices and the special case when the geometric multiplicity of an eigenvalue is less than the algebraic multiplicity. And as I go along, I will give you 4 theorems. So let's get started. And first of all, we're given a linear map F from Rn into Rn. And it is given by its mapping matrix. And it's in standard coordinates, so it is from E to E. And then if we have a new basis, V1, V2, and Vn, so say is a new basis for Rn, then the mapping matrix for this in this new basis from V to V is you have to change from V coordinates to E coordinates. Say we have our mapping matrix V to E. So we have the change of base matrix from V to E, and then we have the change of base matrix from E to V, and this is the same matrix or the inverse of this matrix here. So that will be e to v like this. Now, in the case, if the V base is an eigenbase, that is, if the columns in, or the V base here is an eigenbase, then this mapping matrix is a diagonal matrix with the eigenvalues in the diagonal. Okay, and you see when you have such a basis, then the eigenvectors is in a specific order. So the order matters. You cannot just flip some of these vectors here, then you will get a new basis. But in this order, and then the eigenvalues will appear in the diagonal in the same order as the eigenvectors here. So this is the mapping version of this. And now to the matrix version. We have two matrices. A and B. A is similar. This is a definition. I'll return to this later on. But A is similar to B if a regular matrix exists so B is equal to the inverse of V times A times V. So this is a definition. If you can find a regular matrix such that if you post-multiply by this matrix and pre-multiply by the inverse of this matrix and you get B, then they are similar, the two matrices. And here, if the matrix V consists of eigenvectors, then the matrix B is a diagonal matrix with the eigenvalues in the diagonal. You see, it's quite similar to when you have a mapping and you are considering the mapping matrix. It's quite similar to this relation here between matrices. Again, order matters. If you have say, the eigenvectors in this matrix ordered in a specific way. So you have the first eigenvector in the first column and so forth. Then the order of the eigenvalues in the diagonal will be the same as this order. Okay, so what is really the subject of today? Let's write this down. Today's subject is when is diagonalization possible? So when can you make a change of base, or really a change of base, such that the result will be a diagonal matrix, either if you have a mapping or you have a matrix? Then we're going to discuss this. When is it possible? And here I will start by giving you theorem 1. And it says that an n by n matrix A is, or can be diagonalized if it has an linearly independent eigenvectors. So if there are n linearly independent eigenvectors, then you can you can form this this regular matrix V here, and then you can find a diagonal matrix by applying this this matrix V on A. So let's see that in an example. And this will be this matrix here. You have A is equal to 4 minus 1, 0, 4 minus 1, 0, and then 0, 0, 2. This is a special matrix because the determinant of this matrix is, well, if you make an expansion along the third row here, then you get 2, and then the determinant of this submatrix, or you can say they have 2 identical rows, so the determinant is 0. So it's a singular matrix. But what does that mean in terms of eigenvalues? It means that A and then 0 times E is also 0, because then you're only adding zeros to A. So you can see here that 0 is an eigenvalue for this specific matrix. So let's just look at it. You can see in order to get this mapped into 0, you could put a 0 here, because and if you have something here, then the product with the last row here will be 0. So this is okay. And in order to eliminate these ones, I could put a 1 here and a 4 here. Then I get 4 minus 4 and plus 0. So this is okay. So 1, 4, 0 is an eigenvector corresponding to the eigenvalue 0. So I have here that, and the corresponding eigenvector is 1, 4, 0. Let's look at the next. Of course, you could actually do the characteristic matrix, do the characteristic polynomial, and solve that, and then solve the resulting homogeneous equations. But let's look at it, and we can find a solution. If you take a vector here with 0 at the 2 first positions, then you will get 0 at the corresponding positions here and here. But here you will get the value 2. But this is equal to 2 times 0, 0, 1. So you can see that this vector here, 0, 0, 1, is an eigenvector corresponding to the eigenvalue 2. So I have that lambda 2 is equal to 2, and then this will be 0, 0, 1. Let's see if we can get the final one. We have 4 minus 1, 0, 4 minus 1, 0, and then 0. If again we choose 0 here, then this should be okay. These are similar. What if we take these two values here? Then you get 4 minus 1, that is 3, and 4, 3 here. But this is 3 like this. So again, you can see here that this vector here is an eigenvector corresponding to the eigenvalue 3. Is 3, and corresponding eigenvector is
Sorry, Jesper, what exact method are you using to calculate that? So you're plugging in 1, 1, 0, and then when you do that, it gives you what exactly?
Yeah, well, it's something you can do for this special case. I won't recommend that you do it generally, because it has a special structure. Then you can you can find these eigenvalues and eigenvectors in this particular case. I hope that I have convinced you now that these are eigenvalues and corresponding eigenvectors, because they fulfill this equation here. But if you should do it, then you should do the characteristic polynomial, find the eigenvalues, and for each eigenvalue you will solve the corresponding homogeneous problem in order to find.
Yeah, like we did last week, but this is.
Yeah,
this
I'll do that later on in another example.
To do that.
Okay.
Do this.
Okay, but anyways, you have these three eigen values and corresponding eigenvectors. And so you could ask, are they linearly independent? And you can just form the matrix of these vectors here, and then you can, for instance, take the determinant. And if this is different from 0, then they are linearly independent. But there is a theorem that you can apply. And let me show you this. So this is the second theorem today. We assume that the matrix A has k different eigenvalues. Remember, A is an n by n matrix, but k of the eigenvalues are different. And this means that you have k eigenspaces. So say here you have E lambda 1. Here you have E lambda 2, and so forth. Here you have E lambda k. So you have these eigenspaces here corresponding to the different eigenvalues. And then to the theorem. Eigenvalues from different eigenspaces are linearly independent. So if you choose a vector from this eigenspace here, a vector from this eigenspace, then the two vectors will be linearly independent. So at least if you have k different eigenspace or different eigenvalues, you can find k linearly independent eigenvectors. But you need n. Sorry?
Sorry, is that supposed to say eigenvalues or eigenvectors from different eigenspaces?
If I choose from this, then it's a vector space of vectors. So there will be eigenvectors corresponding to this eigenvalue.
I think he means underneath where you wrote eigenvalues, where you wrote eigenvalues instead of eigenvectors.
Sorry. Thank you. My fault. So it's eigenvectors that, of course, are linearly independent. Thank you. But this means that when you look at this problem here, you have three different eigenvalues. Then you know in advance that these three vectors are linearly independent. You need not check it. And this means that V1, V2, and V3 are linearly independent. So if we put V equal to 140. This was the first of the eigenvectors, and then the second 0, 0, 1, and the third is 1, 1, 0. Then if you perform this product here, the inverse of V times A times V, you will get a diagonal matrix, and this diagonal matrix will be equal to 0, 0, 0, 0 to 0, 0, 0, 3. That is a diagonal matrix with the eigenvalues in the diagonal in the same order as you have the eigenvectors in your. Yeah.
I just have a quick question. When I compute that for the on Maple, it just gives me back A. And even though I know it should be 0, 2, 0, because you're making the vector with the eigenvalues, I'm just wondering why it doesn't give you that.
So you have actually performed this right now in.
No, previously.
Okay.
For the similar question, because we got asked that to do that.
But didn't you do? If you had this relation here, then you would have A is equal to V times lambda times V. So if you perform this, if you put in this, then you would get A. Or V to the minus first. You would get A. Are you thinking of this computation, or?
I don't know. I assume maybe it's just something I'm wrong in my previous computation.
Did I do it correctly? Okay, good. Okay, yeah. Okay, let's take the second example. Example 2. It is, we have A is, I have it here as well, so 1 minus 2, 0, minus 1 plus 1, minus 2, 0, 1, 1. So, what we're going to do now is that we're going to find the eigenvalues. And we do that by taking the characteristic matrix, that is 1 minus lambda, minus 2, 0, minus 1, 1 minus lambda, minus 2, 0, 1, and then 1 minus lambda. So if I say take an expansion along the last column, then I would get 1 minus lambda, and then the determinant of the submatrix you get by eliminating the last row and the last column, you get minus 2, minus 1, 1 minus lambda. And then, and let's take the sign plus, minus, plus, minus. So it'll be minus, minus 2, and then the determinant of the submatrix that you get when you eliminate the second row and the third column, that will be 1 minus lambda, minus 2, and then 0, 1. One minus lambda, and then I evaluate this determinant here, I get 1 minus lambda squared, and then minus, 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 that is minus 2. And here I get minus, minus, that is plus 2, and then this determinant is 1 minus lambda. So you see, if you multiply this in, you get minus 2 times 1 minus lambda plus 2 times 1 minus lambda, so they cancel, and you end up with this determinant here, 1 minus lambda. And this means that you have only one eigenvalue, but it has the algebraic multiplicity 3. So what we're going to do now is that we're going to find the eigenspace, that is the space of eigenvectors corresponding to this eigenvalue. And in order to do so, I form the augmented matrix. When I put in my lambda equal to 1 here, I get 0 in the diagonal. And I keep the rest, minus 1, minus 2. And then I have a 0, minus 2 here. And then I have a 0 and a 1 here. And then the right-hand side, it's a homogeneous problem. So it looks like this. You can see that these two are proportional. So if I interchange these two, what you can do is you can immediately write down the totally reduced matrix, because if you put this as the first one and change the sign, and here this as the second one and divide by minus 2, you get a 1 here. And the third one is, you can subtract the second one, so you have this this matrix here. So you get V1 is equal to minus 2 V3. That is, if you have your V1, V2, V3 coordinates of your eigenvector. And then you have that V2 is equal to 0. So you have one free parameter corresponding to the rank of this matrix being 2. And you have 3 unknowns. So you can then write down the eigen, or the solution to this system, and it will be the free parameter. And then V3 is the free parameter, so that'll be a 1. V2 is 0, and V1 is minus 2, like this. So this eigenspace is then the span of this vector here, minus 2, 0, 1. So you see here that the geometric multiplicity is equal to 1, and this is less than the algebraic multiplicity, which is 3. And in that case, you cannot diagonalize your matrix, because you have only one eigenvector, and you need 3 in order to diagonalize your matrix. So A cannot be diagonalized. Well, still another example. That is example 3. And now A is given by, I have 2, 0, 0, 1, 1, 2, 0, minus 1, 4. And again, find lambda. Subtract lambda from the diagonal elements. 1, 1 minus lambda. 0, and then minus 1 and 4 minus lambda. You have the first row has only an element different from 0 in the first. So this is equal, and then to the determinant of 1 minus lambda, 2 minus 1, 4 minus lambda. So this will be 2 minus lambda, and then it'll be 1 minus lambda times 4 minus lambda, and then plus 2. So it will be equal to 2 minus lambda, and then you get lambda squared. And then you get minus 4 lambda, minus 1 lambda, that is minus 5 lambda. And then you get 4 plus 2, that is plus 6. And you want to find the roots in this polynomial, this characteristic polynomial. And use the 0 rule. You have that, or you have this factor here, and then you can factor this. The product of the roots will be the last one here, and the sum of the roots will be this coefficient with opposite signs. So it will be lambda minus 2 times lambda minus 3. I guess you know this rule. If not, let's take it. If you have 2 roots in a quadratic polynomial, you can call it R1 and R2. And then if you multiply out, you get lambda squared. Then you get minus R1 and times lambda plus R2 times lambda, and then you get plus R1, R2. So the product of the roots is 6, 2 times 3, and then the sum will be equal to this term here with opposite sign. So this is it, and you have that A has 2 eigenvalues, and it will be lambda 1 equal to 2 with algebraic multiplicity equal to 2, and then lambda 2 equal to 3 with algebraic multiplicity equal to 1. So if you sum these, you should have the dimension of the problem. 2 plus 1 is 3. When you have the algebraic multiplicity equal to 1, then you know you can find an eigenvector for that problem because you have this eigenvalue. So the geometric multiplicity of this eigenvalue will be 1. So the question is, are there one eigenvalue corresponding to this, or eigenvector corresponding to this eigenvalue, or are there two? Or is there one, or are there two? Okay, let's find out. Again, we take the augmented matrix. So I subtract 2 from the diagonal, then I get a row of all zeros. And then I get 1, minus 1, 2, and 0. And then 0, minus 1, 2, and 0. So if I could write down, I guess, directly the totally reduced. I interchange the rows, so I take this first. I get, or let's do it in 2 steps. I interchange these rows, so I have 1, minus 2, 0, and then 0, minus 1, 2, 0, and then finally this one. And what I can do then is, if I subtract this from this, I get zeros here, so I get the totally reduced matrix as 1, 0, 0, 0. And then I change sign here, I get 1, minus 2, 0. So you get that V1 is equal to 0 from the first equation, and then you get that V2 is equal to 2V3. So you have one free parameter, that is S. This, that is V3. So you get V1, V2, V3 is S times this vector here, S times 2, and then times 1 here. So you have only one eigenvector. So the geometric multiplicity of your eigenvalue is 1. And this is less than the algebraic multiplicity of which was equal to 2. So if you count the number of independent eigenvectors that you can actually get from this, you can only get 2. And A cannot be diagonalized. And I will sum this up into two theorems. Theorem 3. It says that the geometric multiplicity of an eigenvalue is less than or equal to the algebraic multiplicity of this eigenvalue. Also, you have that this is always greater than or equal to 1. So if you have the algebraic multiplicity equal to 1 for a specific eigenvalue, then you know you have the same geometric multiplicity equal to 1. Theorem 4. If a lambda, or the one eigenvalue of 1 lambda, exists so that Gm, that is a geometric multiplicity, is less than the algebraic multiplicity, then your matrix cannot be diagonalized. And you saw an example of this here. You have the geometric multiplicity of 2 is less than the algebraic multiplicity. So, and this is why when you're investigating this, then you should take the case where you have an algebraic multiplicity that is greater than 1 and see what the geometric multiplicity is in that case. Okay, and I have the last example. I have here A is equal to 0, 1, and 0 minus 1, 0. And you want to find the eigenvalues, form the characteristic matrix and take the determinant in order to get the characteristic polynomial. Then you get, this is 1 minus lambda, 0, 0, and then minus lambda here, 1, and then you get 0, minus 1, and minus lambda. Again, you have a row here with only one element different from 0, and then you get the determinant of this submatrix minus lambda, 1 minus 1 minus lambda. So this will give you 1 minus lambda, and then times lambda squared, and then plus 1. So, and here the roots are plus I and minus I, so you have lambda minus I and lambda plus I as a factorization. So this equal to 0 gives you the 3 roots or the three eigenvalues. The eigenvalues, and this is 1, I, and minus I. So let's find the eigenspace corresponding to the eigenvalue I. We have the augmented matrix, and I put I into this characteristic matrix. 1 minus I, 0, 0, and then I get 0, and then minus I, 1, and then I get 0, minus 1, and then minus I, and the right-hand side. So this is what I'm going to solve. I take R1 and divide it by 1 minus I. And then here I multiply this equation, or this row here, by I. And then I get that this is equivalent to 1, 0, 0, 0. And then I get 0 here, and then I get 1, I, 0. And you see, and then I get and then if I add R2 to R3, I get my fully reduced matrix as 1, 0, 0, 0, 0, 1, I, 0, and then 0, 0, 0. So what I get is that I get B1 is equal to 0 from the first equation, and from this equation here I get that V2 plus I, V3, is equal to 0. So I have one free parameter. I choose V3, and then I get that 1 is 0, V2 is minus I, V3 is equal to a free parameter, and so this is minus I times the same free parameter, and I have an eigenvector corresponding to I here, that is 0, minus 1, 1, or minus I and 1. So if I choose this to be, or I just write, for this eigenvector, I get the eigen, or for this eigenvalue, I get the eigenvector 0, minus I, comma 1, and for this eigenvalue, I get 0, comma I, comma 1. That is, remember, we had a polynomial that we should solve. It is a polynomial here with real coefficients. And so you know that if you have a complex solution to this polynomial, then the complex conjugate would also be a solution. And you find that you have I and minus I as solutions. But the same applies to the eigenvectors. So if you have an eigenvector here, then the complex conjugate of this eigenvector is also a solution. But again, you know that you have 3 different eigenvalues. And this means that the corresponding 3 eigenvectors are linearly independent. So you have your 3 linearly independent eigenvectors, so you can simply diagonalize this matrix. So A can be diagonalized. Well, let's return to similar matrices. We have a definition here. So A is similar to B if a regular matrix exists such that, and I call a regular matrix V exists such that B is equal to the inverse of this regular matrix times A times this regular matrix, then these two matrices are similar. So A, or I should write, if A is similar to B, then B is similar to A. And this is easily shown because you can multiply this by V on the left. And so this is equivalent to V times V times like this. And if V is regular, so is the inverse of V. So this is easy. Take this other one here. Here I have, if A is similar to B and B is similar to A, or B is similar to C, then A is similar to C. And a special version of this is that if C is a diagonal matrix, if A is similar to B and B is similar to a diagonal matrix, then A is similar to this diagonal matrix. And now the final one. Take it here. And this is if A and B are similar. They have identical eigenvalues with equal algebraic multiplicity. I abbreviate that, AM. And this is operational if you want to check if two matrices are equal, then find their eigenvalues and count the multiplicity of the eigenvalues. And then you can decide whether the two matrices are similar. So this was all for now, but do the exercises and then you can do the weekly test. Okay, thank you.
Or is data